Tejas, shall we start today?
Yeah. Hi, I'm Shahir, and I will be presenting HemAIDX to you. Now, I had an elaborate opening planned for this project, but today I think I'll go with a story. A few weeks ago, while we were collecting data for our project, we ran into the problem that one of the hospitals didn't have their analyzers working, which meant a delay of an entire day to get our reports. Once we did get our reports the next day, we had to take our samples to the pathology lab where they were set under processing, and it took about 2 days to get those processed and ready for analysis. When we finally got our slides and reports on the 4th day, we analyzed them and we found out that the patient had leukemia. This delay and this story, I believe, highlights one of the basic challenges of diagnostics in Pakistan, which spends a mere 1.2% of its GDP on the public health sector. In a country with 13.2 million doctors, a mere 1% are pathologists, meaning 2.6 pathologists per 1 million people. A country with 236 million people has just 1,200 medical laboratories, most of which are in the urban areas, while 62.7% of our population lives in rural. Speaking of rural areas, 30% of the samples collected from rural areas end up being contaminated. This delay in diagnostics poses a critical health risk and contributes to increasing the mortality rate. Moreover, frequent road closures in Pakistan, as well as subpar road quality, makes transportation difficult and leads to damaged, delayed, or degraded samples arriving at the testing facilities. A large part of Southeast Asia faces diseases like thalassemia, leukemia, malaria, and anemia. In Pakistan alone, there are about 6.7% patients of thalassemia. Malaria is the 5th leading cause of death, and in 1 in 5 women are anemic. Diseases like this require timely diagnosis for effective treatment. Yet, we're faced with the sad reality that patients require a turnover time of multiple days just to get the report. Delay that could mean the difference between life and death. Analysis shows a significant patient-to-hematologist disparity in Pakistan, with limited hematologist resources posing a great load on the challenges of timely blood sample analysis. As the current blood sample analysis process stands, samples are collected, blood films are prepared from those samples, they are then transported to a laboratory where they are clinically processed, analyzed, and then a report is generated. This entire procedure usually takes around 3 to 4 days to be completed, as it requires some time for the chemical stains to dry out and cure. Even if transport is not included, let's say you are at a main laboratory, you still need a trained hematologist or a pathologist and a technician on site to process those slides, and it still requires at least 3 days to get those reports. Now imagine, what if you could do all of this in seconds? What if all you needed to do to stain your blood samples was to take a picture of it? Reducing the transport costs, removing all the labor and the risk of contamination. Ladies and gentlemen, introducing HemAIDX, an intelligent portable pathology lab. Here's an idea of how it works. We collect samples, slides are prepared, these images are required of the unprocessed blood samples. They are passed through our generative AI models to process them. These images are then zoomed in, cells are isolated, patches are made of those isolated areas, which are passed through our classification module, which recognizes those cells, and then those entire patches are stitched back together to rebuild the original cell. This analyzed and classified cell is then passed on to our deep learning module, as well as trained medical experts for verification and analysis of our report. Now let's see how this magic actually happens. Our project starts with data collection. we collect unprocessed, unfixed blood smears from tertiary care centers in Pakistan, along with their analyzer reports. These are then taken to NUST School of Health Sciences, whose pathology lab is attached with us. Over there, we acquire images of processed and unprocessed slides at 40x magnification through our smartphones using a mount that we have developed ourselves, and this is a patented design. We have an IPO in Pakistan. Then these pairs of images of the processed and unprocessed images are, this is the mount design, and this has been developed in such a way so as to allow any smartphone to be able to easily be attached to any conventional microscope. It doesn't matter where your cameras lie, it doesn't matter how high or how small or tall your phone is. The data pre-processing pipeline is where the most difficult things are come to pass. As the images that we are taking of the processed and unprocessed images are at different points in time, usually days later, because that's how long it takes to process them. It is quite subjective to take accurate images of where the initial images were taken. As such, we have to make sure that our images are aligned so we can get most of the features out of them. So for that, those patches, those pairs of processed and unprocessed images are passed through our aligning algorithm, which aligns those in order to ensure maximum overlap. They are then passed on to our patching algorithm, which patches them into 512 by 512 pixel images. These images are then passed on to a generative AI model. This model is trained on that paired data and learns how to create those processed images by just looking at the unprocessed ones. These images are, after being processed, they are then passed to our detecting algorithm, which is running on a ResNet backbone and utilize an encoder-decoder setup along with prediction heads to identify the types of cell that are present in the image and generate confidence scores at how accurately it can detect those cells. Currently, we have been able to identify all types of white blood cells as well as platelets present in the blood with an accuracy of about 82%. And this is just an average accuracy, a multi-class accuracy. As you can see, the class-wise accuracy is much higher for every single class that we have been able to detect. Our project utilizes attention-based segmentation to break down the cell into its three major parts: the nucleus, cytoplasm, and background. And these features are then utilized to identify the type of cell that is present. We utilize the technique of rule-based disease diagnosis to figure out the disease, what disease the patient might be suffering from. For that, we are in constant collaboration with medical experts who help us understand the morphological elements that go into figuring out what a disease looks like under the microscope. These cues and clues are then passed on to our model, which then eliminates each disease according to those rules until we can accurately figure out what disease the patient is suffering from, and that disease is then printed into a final report. And we'd like to thank the Nuclear Medical Oncology and Radiotherapy Institute as well as Pakistan Institute of Medical Sciences for their medical as well as sample help, NUST School of Health Sciences for giving us access to their research resources as well as their pathology lab, RiceTech for their help in our marketing as well as technical, as well as Metropole Labs for guiding us into helping make this dream into a reality. As it currently stands, the pathology market is a $6-10 billion market by 2030, and we can easily get even a 1% part. If we can get part of it, it's a significant amount. In Pakistan alone, there is a huge market for this project, and definitely our project is promoting the constraints of green AI, promoting the reduction of chemical waste, lowering energy consumption, ensuring water conservation and efficiency, and supporting sustainability goals. Thank you.